start coding and then share my screen with you. So the screen is shared, and I assume like all of you can see my presentation right now. If you cannot see it, please let me know. Right now, yesterday we talked about Kepler's laws, and we applied Kepler's law to find different parameters or different distances. Like for example, we can use the Kepler's third law to find the orbital periods and the semi-major axis length, those kind of things. And we did some examples yesterday, and in fact 2 examples we did, and then we moved on to the Newton's laws of motion, and I explained very briefly about the Newton's gravitational law and angular momentum, those kind of general concepts that we used to have for the in physics, because they will be directly applied here for the motion of planets. And also we talked about the different form of a Kepler's law. Once the Newton found this Newton's laws, he based on the Newton's laws, there is another Kepler's law that is called modified Kepler's law. And we actually talked how modified Kepler's law is related to the Kepler's law that we previously derived. And keep in mind that these Kepler's laws are very important, right? So you should have a very good idea what are the units that you should use. Units are very important, and how this modified Kepler's law and the Newton's version, which is basically the Newton's versions of the Kepler's law, is connected to the original Kepler's law, right? So those kind of things, right? So the last time, so I stopped right here, and we discussed about the shapes of the orbits of different kinds of objects that we can see in our solar system. Now, one thing to notice here is, if you look at, so there are orbits of 3 different objects that I have shown here in the diagram, and you can see that the black color orbits are the orbits of the planets, and they are almost circular, right? So their ellipticity is very small, so which means they are very close to circular orbits, even though they are elliptical orbits. Now if you look at some of these pictures in the internet that you used to see about the orbits of the planets, they are actually exaggerated images that shows you these elliptical paths, right? So actually in actual situations, these orbits are not that much elliptical, right? So they are elliptical orbits, but the ellipticity is very small, as we discussed yesterday, right? So you don't have like these large elliptical shapes for these orbits as you see in these beautiful pictures in the internet, right? And secondly, you can see these the blue color orbits, which are a little bit, if you look at the ellipticity or the elliptical shape, they are somewhat more elliptical compared to the orbits of the planets, right? Now these are actually orbits of the asteroids, as I have mentioned here. Some of these famous asteroids that I have mentioned here. So the orbits of the asteroids are a little bit more elliptical in terms of their shape. And then the other kind, which you can see from the red color, are actually comets, right? Now, one of the 3 famous comets that I have shown here, Halley's comets and 2 other comets, so they are very more elliptical compared to the other 2 types, right? So there is a difference between the orbits in terms of the type of the object, right here. Right. Now then after that we started talking about, so that was about, the natural objects, or the objects that are already existing in our solar system, that is our planets, and then asteroids and comets, right? And of course, there is sun and moon also in our solar system, which we will talk separately in the next chapter. And apart from that, there are instruments or satellites that are sent to the space by man or humans, right? So that's a different story. And so this is where I stopped yesterday. And so there are thousands of satellites that have been placed into the orbit around the Earth. So there are a large number of satellites that are going around the Earth. And we used to tell that most of these satellites are launched into the low Earth orbit, right? So they are on the low Earth orbit. That is because the amount of energy that you need to send these satellites are minimum, right? So that is just to save energy. And typically there are around 50 satellites we used to send to the space in each and every year. And apart from this, there are spacecrafts that we use to send to different planets and the moon, right? And they are also to asteroids, right? So you will probably hear sometimes in the news from time to time that there will be spacecrafts that we use to send to these different planets, right? And remember that there is a difference of sending spacecraft to the other planets and the satellites that are orbiting around us, right? So we need to look at those two things in two different ways. So that is my aim in this section, just to show you what is the main difference in terms of the physics or the speed that you need to send a satellite to the low Earth orbit, and also to send a space shuttle to the other planets, right? Right. Now, to study about that, if you look at this particular picture, which I have shown you in yesterday as well, you can see that there is a man right here sitting on the earth, and he is trying to send a bullet. Let's say he has a gun and he fires a bullet, and depending on the speed of the bullet, maybe if the speed is VA, which is the smallest one, the bullet will go far away some distance, and due to the gravity, it will fall down to a particular point, right? So this is obvious now. And if you increase the bullet, it may go up to a little bit further, right? A point somewhere like here. And if you give a certain amount of velocity that is a little bit greater than VB, then there may be enough speed for that particular bullet to go around the Earth, right? And this is pretty much similar what happens to these low Earth orbit satellites, right? Now the figure right here shows you the pieces of orbital debris that are being packed by the NASA in Earth's orbit. So there are a large number of space debris now in the low Earth orbit. You can see that in each year, if you are sending like 50 satellites, so there should be a lot of them now in our low Earth orbit, right? So this probably will become a problem now in near future in the space, right? Now, there should be, let me see, I was trying to get some, yeah, that's right here. Right, so I would assume that all of you can see my presentation still. Now, relating to the previous diagram right here, you can see that there should be a specific speed for this particular situation where we see here, if you fire the bullet in that speed, the bullet will start to go around the Earth, right? And let's see what is that speed, right? Now I have mentioned here, if our bullet is given a high enough muzzle velocity, and this is called muzzle velocity, by the way, this is VC, the curved surface of the earth causes the ground to remain the same distance from the bullet so that the bullet falls around the earth in a complete circle, right? So what happens is, if you give a certain velocity, which we called as the muzzle velocity, then the bullet will keep the same distance from earth in each and every place, right? And then what happens is the bullet will go around the earth, right, rather than falling onto the earth. And that is exactly what happens to these low earth orbits in most simple way, right? Now there is a specific speed that we should give for in order for this to happen, right? And this speed is usually called as the circular satellite velocity, and the value of the speed is 8 kilometers per second, right? Now this is a huge speed. If you calculate, this is like in terms of kilometers per hour, this will be a very large number, right? And in fact, this is, remember that this value is different from what you used to learn as the escape velocity, right? So that comes into play in the next section. That is, when we have to send a spacecraft to a different planet, then the story will be different, right? And so we call these kind of spacecrafts as interplanetary spacecrafts. Now, as we all know, this exploration of the solar system has been carried out largely by these robot spacecrafts sent to the other planets, which means they do not have any humans inside these spacecrafts, and all of them are like robot spacecrafts. Now, one of the barriers that we have is that when you need to send a spacecraft to the other planets, you have to achieve the escape speed or the escape velocity. You probably have heard about this, right? Even though you may not have heard about the other one. So we used to talk about the escape velocity frequently in gravitational physics. And this is value of the escape velocity or the speed is typically 11 kilometers per second. Now this is a little bit higher compared to the circular satellite velocity, right? So you just keep in mind and also understand the difference of these two terms, right? So for the escape speed, which means you need to go beyond the Earth, the value will be 11 kilometers per second, right? So you have to give that speed, right? So which is a little bit larger than what you have to give for these satellites, which are in the low Earth orbit. Now, if we wish to orbit a planet, we must show the spacecraft with the rocket. So we must slow the spacecraft with the rocket when the spacecraft is near its destination. So when you get close to, so you have to give provide the escape speed to move that out from the Earth, and then when you need to go for a certain planet or the orbit of that particular planet, you have to slow down the spacecraft at the same time, right? And you have to use a rocket for that when you get close to that particular planet. And so once you slow it down, then that will allow for that particular spacecraft to be captured into an elliptical orbit in that particular planet, right? And then there should be an additional rocket thrust that should be required to bring the vehicle down from orbit of landing on the surface, right? So if you have to send something down to the landing on that surface, there should be an additional rocket to do that, right? So you can see that this is not an easy process. Now, the other thing is, if you are planning to return trip, then this process should be repeated, and there should be another propulsive power for that, right? So this is very briefly is what happens to these the rockets that you send for different planets, right? So this is just like a general procedure that you have to follow, right? And you probably will see in the news that sometimes that you send these spacecrafts and then you collect samples, and sometimes even they send it back to the earth as well, right? So this is the process for that. And actually our aim in this particular course is not to talk about space studies or space science. It's a different subject, but this is just to give you an basic understanding what actually happens, and the difference between sending a rocket or a space shuttle to a different planet, and sending a satellite to our low Earth orbit. Right? These are two different stories. Right. Now, up to now, what we have talked is about the motion of the planets, and then how it is applied, and then how these rockets are sent to different planets, and how the satellites are sent to our low Earth orbit. And so what you should notice up to now is when we talk about these Newton's laws and also the Kepler's laws, we have considered only two objects, right? And each and every time, even when we talk about Kepler's laws, we did not talk about more than two objects, right? Always we considered the sun and another planet, or maybe two planets. That should be okay as well. But most of the time we consider the sun and a particular planet that we are interested, right? And however, if you go into the real situation, these motion of the planets are more complicated than this, because the gravity act mutually be in between each and every object, right? So what that means is, if you try to consider the motion of, let's say, Earth, it will be affected by the sun. Basically, there are other planets around our planet, right? For example, Jupiter, and then you have Venus, Mars, those kind of planets. So they will also exert a gravitational influence or a gravitational force on us, right? So when you look at it in that way, you have to consider more than two bodies, right, in actual situations. And when you need to consider more than two bodies, the things become very complicated, right? And these are actually called many body problems in physics. And you have to calculate these influences in a proper way. And you cannot do it from your hands, and you have to use large computers for those kind of calculations, right? This is something you may not have thought of before, but this is what actually happens, because now when you consider the one planet, so there are other planets who are exerting gravitational forces on it, right? And which means you have to take into account those forces as well if you do an exact calculation. But there is a slight advantage. Let me go and finish this part. Now you need something called supercomputers for these kind of complicated calculations, right? When you need to involve more than two bodies for a calculation, right? Now you may think that why can't you do that? If you have like one planet and there are 8 other planets, then you can actually calculate the total force exerted on a particular planet due to all the other planets, right? And it is true, you can do that. But the problem is when you are calculating it, even during that time, the other planets are also moving into different places. There is a movement as well, like an acceleration, right? So this makes things very complicated. However, up to now, if you look at what we have learned and we have applied it without any issue for our solar system, for example, when you need to calculate the orbital periods, we have used the distance from the sun to that particular planet, and then we have calculated the orbital period, and seems that most of these answers are accurate, even though we did not consider the other planets, right? Can anybody explain why is that? even though we have other planets on the solar system that should exert different gravitational forces for the interested planet. Still, when we use the Kepler's law, just with the one planet and the sun, we are still getting very accurate answers. So, and then why should we bother about this even? Anybody have any idea about that or any answer for that? Right. So if you do not have an answer, let me continue a little bit more into the next section, next two slides, and then we will discuss why is you why do you still get very good answers even just only using the Kepler's laws, right? Now, uh, in right. So this is the last slide of this chapter, but there is a story behind this particular slide, and there are two mathematicians, John Adams, and then there is another astronomer that who lived in this 18th century. So these two astronomers actually are responsible to the discovery of the last two planets in the solar system, that is Uranus and Neptune, right? In fact, when the Uranus was observed, uh, depending on the gravitational influences of the planet Uranus, uh, they were able to predict that there should be another planet Neptune, right? Because those two planets are not visible from the naked eye, but by using the uh, calculations, by applying the Kepler's laws and other these mathematical laws discovered at that time, they were able to predict that there should be another planet called Neptune, and actually they were able to figure it out later, right? So that is an application of what you have learned, and the reason that you don't need to worry about these gravitational influences of the other planets for the time being is that if you consider the sun and the other planet, the mass of the sun is very large, right? Compared to all the other planets. And because of that, even if you calculate the gravitational influences that is coming from the other planets, they are, you can consider them as very negligible amounts, right? But still, there is an effect, right? So now these small effects can be calculated by something called gravitational perturbations. We will not talk about that here, but there is a way to calculate it, right? If you add those calculations, then your answers will be more accurate. But the perturbation means small variations that you can neglect if you need, right? So that this is why you get somewhat more accurate answers even without considering those more, I mean, those motions of the other planets or the effects of the other planets. Right, so let me stop this presentation here, and I'm going to take the other presentation for you, which is about the moon, sun, and our earth. And if any of you have any questions about this particular chapter or anything else, feel free to answer until I get the next presentation here for you. Right. So no questions, at least a single one. So I think that all of you have understood everything what I have told, right? So without any issues then. So let me go back to this particular presentation. So, right. Hold on a minute, please. So I'm going to open up my next presentation. Yeah. Right. So I'm going to share this with you. Right. So I guess you should be able to see the presentation, and so I would highly recommend you that you connect the presentation yourself by using this code as usual, so that you can view the presentation in your machine or the smartphone while I am having the presentation here. Right. Right. So since we have limited time, so while you are connecting to this particular presentation, let me start the presentation. So you will see the code on the top right hand corner. If any of you, I mean, you should actually all should be connected to the presentation, and I will be presenting it in this mode. Now in this chapter, what we will talk about basically about our Earth, Moon, and our sky as well. Right. So remember that from the previous chapters, what we have talked is first we had an introduction about to the astronomy, and then there was a little tour about the universe that we went through, starting from the very small scale, that is from the Earth. We went up to the galaxies, galaxy clusters, and for these large scale structures. And as the next step, we talked about the history of the astronomy and how different some of these different things were discovered at the ancient time. And then we talked about the constellations and how people arranged the constellations and how they used those. And then a little bit about the connection between the astrology and astronomy, those kind of stuff. And then the last few weeks, we talked about this, different, we call this the orbits and the motion. That is about different laws that we have to use to explain the movements of the planets and different objects in our solar system, right? And Now in this chapter, we are going to talk about more details about our own Earth and the moon and our sky, right? So there will be different phenomena that we have due to the presence of the moon on the sky and how the phases of the moons are different phases of the moon that we can see how that happens, those kind of things. Right now to start with, here is an interesting picture. You would see that always I used to give you one picture at the beginning for each chapter, most of the chapters, just to give you an idea what we are going to talk. And this is an image captured with a fisheye lens about at the Atlantic Space Shuttle on December 9, 1993. And the object that you see in the background right here, the large object, is actually the Hubble Space Telescope. And this was taken in 1993 when they went for a repair in the Hubble Space Telescope. And they have taken this image. And you can see that the shape of the Earth is not looks like circular. It's like kind of a little bit exaggerated or elongated, right? So that is because they have used this fisheye lens, and that has a different effect. Now, if there is somebody, if some of you do photography, you probably know what fisheye lens means, right? Fisheye lens is a lens that we use in photography sometimes to give a different appearance or different different shape for your photos, right? So it is the similar situation happens here. That is why you see this. You are looking at Earth from the space, and your image of the Earth is little bit different in terms of its shape, but that is just an effect came from the lens that they have used. Other than that, this image is taken in the month of December, and the reddish color region that you see on the Earth is a continent, and that is Australia, right? So that is a different continent. And you can see that it's on the reddish color because the seasons that you have for the southern hemisphere are completely opposite for the seasons that you have for the northern hemisphere, right? Now in December, that means it should be a very hard winter that you should have for these northern hemisphere countries. For example, countries like North America and Canada, right? And we also feel a little bit of cold in the month of December, but we don't feel it that much. And you will understand why don't we feel it that much from today's lecture as well. And but for the month of December, it is completely opposite for these countries in the southern hemisphere. For example, as you see, a country like Australia, they will have their summertime. So that means they will get the maximum sunlight at that particular time of the year, right? So there are completely different seasons because of that. So that is just to start. And when we look at our own Earth, so there are certain names that we should know in geometry when you talk about the different locations of the Earth. Right now, nowadays, actually, you don't need these details because you have Google Maps and you can just locate everything from your mobile phone. But to do that, you should. I mean, if somebody needs to locate something in the Earth, these are the basics, right? The number one is need to know what a great circle means, right? In geometry, a great circle is any type of circle on the surface of the sphere whose center is at the center of the sphere, right? So which means great circle is a circle, but the center of that circle should be the center of the sphere, right? Now think about a large sphere, and you can make any number of circles on that sphere, but all of these the center of all of these circles should be the center of the sphere, right? So you can make any number of circles in that way, right? And I will show you a diagram in the next slide so that it will be more clear for you. Now Series of great circles that pass through both the north and south poles are called meridian. Right? And if there is a great circle that passes through either the north, not either, passes through both north and south poles, they are called meridian. So it's also a great circle. So you just understand the difference, right? The great circle is any type of circle on the surface of a sphere. The center should be at the center of the sphere. So that is the only condition for the great circle. But meridian is like a subset of great circles. But these great circles should pass through both north and south poles. So there should be an additional condition for the meridian, right? And if you take any point on the surface of the earth, there should be a meridian that passes through it, right? So if you take any, you will understand it from the next diagram that I am going to show you. If you take any point on the surface, you will always have a meridian that passing through that particular object, right? Now, so you need these terms and the locations to define the coordinate system for the earth. Now, all of us know that even the Google Maps, they use the longitudes and the latitudes, right? The longitudes means the prime meridian. The longitude of the prime meridian is defined as 0 degrees. Particular place is at Greenwich, England. And uh, and I think this last part is you cannot see it, but I will explain what that means. I will upload this presentation, right? Actually, the longitude is defined as the number of degrees of arc along the equator between your meridian and the prime meridian, right? So we have defined what prime meridian is, and then you have your own meridian, and if you take the number of degrees between the prime meridian and your meridian, so that will be defined as the longitude, and I will show an example in the next slide. And if you talk about the latitude, that is the number of degrees that you are away from the equator along your meridian. Now let me just next slide and show that. And this is actually the actual Greenwich line that you can see right here, which is the definition to measure the longitudes. And here is an example how to measure the latitudes and longitudes. Now you can see for the great circles, great circle is any circle on the surface of a sphere whose center is at the center of the sphere, right? So that means you can here center should be somewhere at the middle here on the if you consider it as a sphere, you can draw circles to any directions, in this direction, that direction, and in this direction or any kind of direction. You can draw circles, and all these circles will go to at the center of the sphere. So that is the only condition for a great circle, right? But these great circles, all these great circles are not important for us when you define the coordinate system. What you need is you have to consider the meridians. The meridian means circles has to go to both north and south pole, and you can see the white circles that go from north pole to the south pole that that are drawn in this particular diagram, right? So those are actually meridians, and you can see that starting from the north pole, this meridian goes down to the south pole, and it will come again from the other side towards the north pole again, right? And then you can see that like that, you will be on one of those locations on the surface of the earth. For each and every location of the earth, you can draw a meridian, right? So that means a great circle that goes through both north and south pole, right? So I hope that is clear for you what a meridian means. The great circle means you can draw it to in any direction on this surface. That only condition is it has the center of the circle has to be at the center of the sphere, right? Now then, when you need to have the meridian means that great circle has to pass through those south and north poles. Now all these white lines that you see that goes from north to south are meridians, and not only those circles, at any point on the surface here you can draw a meridian that goes through you, right? So that's why uh, that I have told in the previous slide that any point on the surface of the earth will have a meridian passing through it, right? So I hope you have understood that. And there should be a special meridian that we called as the prime meridian, and that is this particular line right here. The prime meridian is defined as the, and that is the line that you can see that these people are looking at. This is the prime meridian line that is drawn on the earth, and there is a special location for here. This is called Greenwich, and this is how the Greenwich time is defined as well. You may have heard about this in your, maybe in your school time as well. And that line is right here, which we called as the prime meridian, and that is usually goes through Greenwich, England. So that's a specific prime meridian line, which we called as the prime meridian, right? And that this is where we started to measure the longitude values. And you can see if you are looking at this particular location, which is the Washington, D.C., when you need to give the coordinates, you have to define the longitude starting from this prime meridian. So this red arrow defines the longitude of the Washington, D.C., the angular distance measured from here to here. And I have mentioned here the longitude is a number of degrees east or west of the prime meridian. So the Washington DC coordinates are 38 degrees north and 77 degrees towards the west. So this 77 degrees towards the west is measured from here to here. So that is the longitude, and the latitude is defined as the number of degrees that you are away from the equator along your meridian, right? So that means the number of degrees, if you are right here, then your meridian line should go from here to here through this red arrow, right? The number of degrees that you are away from the equator is right here, is your latitude, right? So number, how high you are from the equator. So that's how you define the latitude and the longitude, right? So you will, in this particular case, the Washington DC coordinates, the latitude is 38 degrees north and the longitude is 77 degrees west. So you always have to give this direction because, for example, if you go to a country like in this area, somewhere in the Brazil, so that will be number of degrees towards the south, right? Because those countries are located in the southern hemisphere, right? So that's how you locate an object. So I hope you probably now have a good idea about what is a great circle and what is your meridian and what prime meridian means and how you use all these definitions to locate an object on the sky, right? And this is exactly what your Google Maps tells you, right? So this is basically how it tells it, right? Now that is about how to locate the place on the earth, right? Now let's look at how to locate the place in the sky, right? Now, in the same way that you use the location for the locations on the earth, astronomers use a coordinates called declination and right ascension to locate an object on the sky, right? Now, to denote the position of the object in the sky, we do not have any spheres drawn on the sky, so we assume a fixed celestial sphere, which is kind of a projection of our own Earth sphere to the sky, right? Now, the definition is the declination is measured from the celestial equator towards the north or south. So if you measure the declination towards the north, so that will be a positive number. If you measure the declination towards the south, that will be a negative number. Now these measurements are taken with respect to the celestial equator, right? And remember, within the first two lectures, I have defined what is our celestial equator, right? That is basically the projection of our own equator to the sky, right? If you think about an imaginary sphere on the sky. Now, if you take an example, let's say take the Polaris. Polaris is the North Star, which is the star is usually located very near to the North Celestial Pole, right? Now, if you need to tell the declination of this North Celestial Pole star, the declination should be almost plus 90 degrees, right? This is because the star is actually located on the North Pole, so that is 90 degrees from the celestial equator, and it is on the north towards the northern side, so that the value should be plus, right? So you should understand what plus and minus mean. Now, for example, if you look at a star in the southern hemisphere, then the declination value should be minus 90 degrees, right? And on the other hand, so that's how you define the declination of a star or any other celestial object on the sky. If you take the right ascension, that is similar to the longitude that you have measured. Only thing is there should be a slight change to the definition. Instead of starting from the prime meridian, that is the Greenwich line for the Earth, now we have to start with a different definition from a different location. So we measure the right ascension counting from the vernal equinox. Right now, I have not introduced you this word called the vernal equinox before, and therefore I have defined what vernal equinox means. So that is a point in the sky where the ecliptic, so that means the path of the sun crosses the celestial equator. Right now, you will understand this further when I go into the next section when we talk about the seasons. Right, all of us know that with respect to us, there is a movement of the sun on the sky throughout the year, right? So that path of the sun on the sky is what we called as the ecliptic. Basically, the path of the, it is defined as the path of the sun on the sky. Now, this path, the sun normally crosses the celestial equator 2 times per year, right? And one of those points when it crosses the celestial equator, we call that particular point as the vernal equinox. And we are going to use that particular point as the reference point to measure right ascensions. Basically, the value of the right ascension at this particular point will be 0, and we will be measuring everything with respect to that, right? So this is very similar to measuring the longitude on the Earth. So that is why I have introduced you the longitude before. Now, what is vernal equinox? We will discuss about that a little bit more in these coming slides, right? Now, when you need to measure the right ascension, it can be expressed either in the units of angle, so that means in terms of degrees, or in units of time, so that means in terms of hours, and minutes. And so there are 2 different ways that you can explain the right ascension. If you take the connection between the time and the number of degrees, that is basically each 15 degrees is equal to 1 hour of time. And this is based on the fact that our Earth rotates at 360 degrees for 24 hour of time. So that means for each 15 degrees, we will have a rotation of 1 hour. So that is the base for this particular calculation, right? Now, if I give you an example, let's say you have a celestial coordinate of a bright star called Capella. Capella is one of the stars, one of the bright stars actually. Capella, we can tell that the coordinate of the Capella right accession equal to either 5 hours or 75 degrees, and the declination is plus 50 degrees. Now you can see that the right accession, we don't use a sign because we know how it is measured. It is starting from the vernal equinox, and then the declination is plus 50 degrees. So that represents that this particular star should be on the northern hemisphere, right? So that is the idea behind that. Now, right, so just keep that in mind, and let me see whether I can show you some of these examples. So there are online star catalogs and object catalogs in the sky. So let me show you. There is one of those catalogs, and if you go and just to give you an example how these coordinates of the stars are given. So let me just type name of the object, and I can search for that, and there is another option right here which is mentioned as J2000, right? So I will explain what that means later, and let me just search for it, and then you can get all the information about this particular star right here. And I assume that you can see my screen, right? So because I have changed the screen. By the way, can you hear me? I guess you can hear me, right? Okay, right. And you can see that the position of the Capella is given here 5 hours, then 16 minutes and some arc seconds, plus the degrees is 45 degrees, right? And then you have some minutes and arc seconds here, 45 degrees plus something. So this is very similar to, this is how a coordinate of an object is given. This is the standard format, right? So I just need to show you how these are actually useful, right? And there are wealth of other information about this particular star, like measurements taken about the star and all kind of these things that we normally used in our research, astronomy research. But what I want you to explain here is how this is usually used. Now you can see that the right accession is close to 5 hours and declination is close to 50 degrees here in my presentation, which is somewhat close to the actual values, not the exact values, right? Now, anybody knows what is this? You may have heard about this in your physics practical sometimes. We used to do this. This is called focal pendulum, and this is a pendulum that used in a long time ago. Still, this is available in somewhere to prove that our Earth turns, right? Which means Earth rotates our own axis, right? Initially, we didn't know about that, and then they have this focal pendulum, and you can see there are targets located around this pendulum, and when you start swinging the pendulum, and when you have these targets, every hour, if the Earth rotates, this plate will rotate. So that means all these targets will be hit by this particular pendulum during the course of 12 hours, right? So that is the idea. So if the Earth rotates, you should have these targets fallen down like this or hit by this particular pendulum. So this is just a proof that the Earth rotates, right? Because the evidence that the Earth is rotating is important for us in astronomy. When we go into the next phase. Now, what we have talked up to now is how how you can locate a place on the Earth, and at the same time how you can locate a place on the sky, right? And we use basically the right ascension and declination, and then we have defined how these right ascension and declinations are measured, and I have given you an example and showed you in the real database how these are mentioned, right? Now let's go into the next phase to see about talk about a little bit more about seasons, right? So once you go through this particular chapter in certain places, I will explain a little bit more about these vernal equinoxes and those kind of things. Especially they are actually connected with seasons, right? And now when you talk about different seasons that we have during the course of an year, and we don't actually feel it that much, but people in the northern and southern, close to the northern and hemisphere, northern and southern hemisphere countries, they feel it actually. Now, when you have different seasons at different times in the year, at ancient time, people were thinking that what could be the reason for this, right? And so many people believed the seasons were a result of a changing distance between the Earth and the Sun. And to be honest, I mean, if you think about even now, some people think that the reason for these different seasons is the changing distance between the Earth and Sun. Actually, I think this the wrong perception about this came from the fact that when we draw the path of our Earth around the Sun, we make it as a highly elliptical orbit, right? Which is actually not the case, because we are in an elliptical orbit, as I told you, but it is not as elliptical as we thought. So it is very close to the circular orbit, but with a very small elliptical shape, right? And because that we draw it like with a highly elliptical orbit, when we draw it on a paper or something like that, people think that, okay, when the Earth is furthest away, then you have a different season. When it comes the closest to us, then you have a different season, right? But this is actually not the case. You can see that as a fact here that although the Earth's orbit around the Sun is an ellipse, its distance from the Sun varies by only about 3%, right? So the distance will vary only about 3%. You can see that's the amount of ellipticity that we have, right? So the distance, the variations of distance from the Earth to the Sun is very small during a course of year, because of this ellipticity is very small. So this small change is not enough to cause these significant variations in the Sun's heat, right? Because I mean, if this is only 3%, then you will have a very small change for the seasons, but it is not the case, right? What we are witnessing is that, for example, in the time of December, you will get very cold weather in these northern hemispherical countries, especially for the Northern America and Canada, right? So their temperatures drop down to like even -20, -30 in certain places. So that, I mean, you cannot explain that with this 3% difference in the orbit that we have, right? So there should be other reasons for that, right? And the other thing is, Earth is actually closest to the Sun in January, when the northern hemisphere is in the middle of the winter. So that doesn't make sense, no? When Earth is closest to the Sun in January, then you should have then the summer, right? Because Earth is very close to you, no? But it is not the case. In January, we have the winter, right? And all these facts tell us that the reason for having different seasons is not the fact that we are in an elliptical orbit and the distance of from the Sun to Earth is keep changing, right? So that is wrong. So there is no major effect from that. What actually causes the season is this tilt of our Earth axis by 23.5 degrees, and I will explain why. Right, so here is our diagram, and you can see the sun is at the center, and there is Earth at 4 different locations for you, and you can see there is a tilt on the angle of the Earth, and you can clearly see that. Now, even from this diagram, when you draw it, you can see that the Earth looks like far away from us when you are in here and here, right? And it is close to us when you are in here and here. But that is, by the way, not the reason for different seasons. The reason is actually this tilt of the angle that you have by 23.5 degrees, right? And this is the location where you have our Earth at December 21st, right? Now you can see that when you look at these northern hemispherical countries, there is a small, but the amount of sunlight that they will receive is very less because of this angle for this orientation, right? And because of that, you will get less sunlight to these northern hemispherical countries, and that is why you have the winter, if I tell it in brief. But completely opposite thing happens when it comes to June 21st. So June 21st was when it was last, I guess, a day in the last week, right? And that was the time where the summer solstice, which means the summertime starts for these countries in the southern hemisphere, sorry, northern hemisphere. So what happens here is you can see that the Earth is angled because of this tilt. Earth is angled towards the sun, and the southern part is facing now towards the sun, and that is why they get more sunlight in that year, that time, and they will have the summer, right? So which means the temperatures are higher. Now exactly opposite thing happens to the countries in the southern hemisphere. When it is in December, they will get more sunlight because they are, because of the tilt, the southern hemispherical countries will be more closer to the sun, and they will get direct sunlight in that particular time, right? And the opposite thing happens in the June time for them, right? So they will have a winter now in this particular time of the year. They will have the winter, right? So that's how it works. It is, keep in mind that it is not that we have seasons because of these different distances from the sun, right? The distance difference is very small. The primary reason is the tilt of the Earth axis, right? And so I'm just going to skip some of these slides that you can just try to understand yourself. And this is just a diagram. When it comes to the winter, what happens is actually the sun rays doesn't, incident on the Earth directly to these other hemispherical countries. They will be angled like this. So that means the intensity will be less. So that's why they have the winter at that time. Right now, this particular diagram explains you the path of the sun for different seasons. Now, let's say, for example, if you take the sun's path on June 21st, now this is assuming that we are stable, and with respect to us, the sun is moving around, right? So the path of the sun is with respect to us. So we are right at the center. Let's say we are right here, and look at the path of the sun, right? Now here is the north celestial pole, and this is the angle, the tilted angle of 23 degrees. And then you can see for the northern hemispherical countries, the sun is up from here up to here. So they have a long daytime on June 21st. I think, in fact, the longest day for them. Now this, the how long is the day depend on where you are, because for the people who are on the celestial equator, we will not feel it that much, right? So we will have equal day and night times in most of the time. But if you are in the northern hemispherical countries, For example, in this time of the year, you will have the sunlight until 10 p.m. sometimes, even until 11 p.m., right? And there are certain villages or towns that I know that are very close to the northern hemisphere, that they even don't have a night time. So the whole 24 hours, they will get the sunlight. For example, if you are in the North Pole during this time, you will get sunlight for the whole 24 hours, right? So the sun will not set, right, for those places on the northern hemisphere. And exactly opposite thing will happen to these people in the southern hemisphere. As you can see here, there will be no sunlight at all for this particular part, right, during the 24 hours for the southern pole. So there will be villages that you never get sunlight sometimes, right, for this at this particular time. And even if you go and even search in the YouTube, there are videos about these how people live without sunlight for few months sometimes, even in certain places in the Alaska. Alaska is very close to the northern pole, so they have certain cities, and one city that I remember is called Barrow, Alaska. And if you go and look at search it, so there are certain period of the time that they don't even get any kind of sunlight. So you have only the night time, right? So it is very difficult to live, but still people are living there. So that is what happened. Everything happens because of this tilt of the earth axis, right? Now this is what happens on the June 21st, and you can accordingly understand what happens on March and September. Because March and September is the time where the path of the sun crosses the celestial equator. Now in June 21st, you have the sun in the northern hemisphere. Then what happens is when it comes to the September 21st, that means probably 3 months from now, the sun will move towards the equator. Then what will happen is we have direct sunlight then. So that this is why you get a lot of heating and sweating on this time of year around, when it comes to early September, because we are a little bit above the equator. Before it comes to the equator, we will feel it. Early September, you will get a lot of sunlight here, and you get a lot of heating and sweating, and it's hard to stay outside for us as well. So that happens due to the fact the angle of the tilt of the earth axis, right? And when it goes to the December, that means 3 months, then the sun will move on down towards the southern hemisphere, and then you don't have much sunlight directly come to you. And this is why even in the months of December, even for us, you don't get much heat, so we feel a little bit cooler in those December months. But when you go to these northern American countries, they feel it a lot, right? So they have a lot of like less temperatures on that particular time of the year. And then once again, what will happen is after December 1st, then the sun will start to come again towards the equator, right? And the sun will cross the celestial equator on March 21st again. And this is why again, when it comes to March and April time, we get a very hot weather again, right? And then it goes to the celestial equator, and then we move towards the northern hemisphere. Now this point right here, so there are 2 times, as I told you, that the sun crosses the celestial equator, and one of those points we called as the vernal equinox, right? So that is March 21st. And these are some diagrams at how this sunlight hit on the earth depending on the different times of the year. You can see that in the December, most of the sunlight hit towards the southern hemisphere, and the intensity that you get for the northern hemisphere is less. So that's why you have the winter like that, right? So that is how the seasons occur. And so let me show you another aspect of this, the movement of that happens due to the movement of the earth and sun. So that is sidereal day and solar day, right? Now most fundamental astronomical unit of the time is the day, right? So we know that we have 24 hours for our day, and this day is based on the rotation of the earth. So based on how earth rotates, And if you consider a solar day, so there are two definitions here, keep that in mind. So that is the solar day and the sidereal day. If you consider a solar day is slightly longer than the sidereal day, right? Or we used to tell that sidereal day as well. Now, the reason is actually Earth has to rotate an additional amount equal to 1 over 365 for full turn, right? And the time required for this extra rotation of a day is about 4 minutes. So therefore, a solar day is 4 minutes longer than a sidereal day. And let me explain it to you from this particular diagram, because this is very important if you are observing the sky, right? So this time difference, you have to consider it always. You can see that here is our Earth, and if you consider this star that is so far away, you can see that when Earth rotates a complete circle, then we used to tell that it as a day, right? But what happens is Earth is going around the sun also, no? In one day, it moved from here to here, so that will be 1 degree, right? Out of 365 degrees. Now, when Earth moves from here to here, from day 1 to day 2, if you consider the sun to have, let's look at this particular red arrow right here. If you want to face the same point towards the sun again after the next day, what you have to have is Earth has rotated 365 degrees when it comes to this line. However, since the Earth has moved from here to here as well, you have to rotate the Earth by extra 1 degree in order to face the same location towards the sun, right? That complete that particular circle. So that is due to the fact that you have to rotate this extra little bit amount because of the movement of the Earth on its orbit, right? Now, this is the difference between the sidereal or sidereal time and the solar time. So solar time, for the solar day, you have to rotate extra little bit amount, right? And astronomers usually prefer sidereal time or the sidereal time of planning their observations. Because in that system, the star rise and set at the same time every day, right? So that is the condition. But right. Now I am going to, if you understood this, I am going to ask the question based on this, which is a very practical question. So let's see whether you can answer for this question, right? So here is the question. So I will give you a few minutes for you to think about this and give me an answer. So you should be able to type an answer in using your mobile phone or everything. So it is okay to get wrong answers, right? So just try it, because in that way you can understand this very clearly, because this is something very important for you if you are going outside and look at and try to watch stars from given location. So that, let me see whether this is, I think this particular question is not completely printed here. So let me just have this little bit clear. I'll change it. So let me read you the question, because there is a part of the question that is not printed here, so that you can answer, right? So you assume that there is a bright star, let's say the Sirius, right? So all of you know about Sirius, and this star Sirius at 7 p.m. from a given location, so that by midnight it is very high in the sky. So what that means is, uh, so the star Sirius will rise at 7 p.m. So that is uh, the sentence that is not printed here. Assume the bright star Sirius rises at 7 p.m. from a given location, right? So you have to assume that there is this bright star Sirius which will rise at 7 p.m. From a given location. So let's say you are at home and you see that the star Sirius rises from the eastern horizon at the 7 p.m. Right? So that's what you have to assume. And then what you need to find is, so the advantage is when you see that the star rises at 7 p.m. around by the time that you have the midnight, you should be able to see the star right above your sky around that region. And the question is, at what time will the Sirius rises in 3 months? After 3 months, at what time the Sirius would rise? So that is the question, right? So this is based on this concept or the thing that we learned about the Sirius. Sorry, about the sidereal time and the solar time. So let me give you, let's say, 2 minutes to think about this. Once again, what is missing here is that the star Sirius rises at 7 p.m., right? So that is from a given location. So the question is asking after 90 days, what time will this particular star will rise? So that is what you have to find. As you can see that these kind of things are very important for you to know, right? So if somebody asks, let's say a school student is asking as a university student who did an astronomy course as well, school student come to you and ask this question, then you should be able to answer that, right? It seems to you like a simple question, right? And this is based on this concept about the sidereal time and the solar time. So just as a hint, think about there is a difference of time. So that difference is like 4 minutes. So that is what you have to take into account. Now, each day there will be a 4 minutes difference between these two times, right? Great. I have one response. Good. So how about the others? Right, so I will show you the response that I have, because it seems like, so the answer that I have is this one right here, 360 minutes. And thank you for the students who gave the answer. The answer is actually somewhat correct. And let's see how you can calculate this. Right. Here is the answer, right? Now, in 3 months, what will happen is series will be rising earlier by this much of minutes. So that's because for each day, there is a delay in 4 minutes, right? You can see that if you look at this diagram, to point towards the sun, you have to rotate extra 1 degree. So that will be equal to 4 minutes, right? So that's what you have here. Okay. So that is 4 minutes per day. So what will happen is, if you multiply 90 days by 4 minutes, that will be equal to 360 minutes for 6 hours. So that means if you see this particular star rises at 7 p.m. today, after 3 months, this particular star will rise 6 hours earlier. So that is at 1 p.m. Right? So that means at 7 p.m. you should be able to see this particular star high in the sky, right? When the sun is setting, right? And so this is a good example that how you apply the things that you are learning, right? To observe the sky, you should have this idea, right, at least. So you will even now, I told you that there are a number of planets visible on the sky, right? Now you can decide after 3 months if you are going to look at the same orientation, whether you will be able to see all these planets or not, right? What planets that you will be able to see and what constellations that you will be able to see. Even without having a sky map or anything like that, you can just decide about those based on this information, right? Right, now let me, right, the time is 9:28, and so there is another example right here. If a star rises at 8:30 p.m. tonight, approximately what time till will it rise 2 months from now, right? So that is again the same kind of an problem. So just practice it when I share it. So that is 4 hours earlier. So that will be 4:30 p.m. And so there is a definition for the international date time, which I'm not going to go through. Right, I guess our time is over now. So let me stop from here, and I will take on the next slide, which is about the moon. So we'll be talking about the phases of the moon and those kind of stuff on the next day. Anybody have any questions up to here? Right. If you do not have any questions, let me now for the next class. Typically we used to do on Mondays and Wednesdays, but depending on the power cut, I will check, right? So there will be no fixed date for the weeks, but anyway, whenever I figure out the power cut table, and if I can do it in the weekday, then I will get another 1 or 2 class in the weekdays as well, right? So in that way we can cover up everything. Basically, I have completed, I guess, around 7 lectures up to now. So you have 30 lectures to do. So basically, I covered what I was to cover in the last week. And for the next week also, I will try to get 2 days from the weekdays. If I cannot, then I will move the lectures onto the weekends. But what I am trying to do is do it as early as possible, right? Without waiting, because then we don't know what would happen, and things will get delayed for you as well, right? So I will update you with the lecture times once I know the power cut schedule, and I will check with you also your power cut schedule. And if I can find a time in between that, then I will probably
schedule the lectures, and that will be most probably in the evenings because I am working here in the daytime as well, right? So no questions, not at least a single question from you. Right, so if you do not have questions, let me stop from here. And by the way, some of the lectures are now available as YouTube links. If any of you couldn't participate, they will be available, right? But I just to let you know, I cannot guarantee that all the lectures would be available like that, right? So there are some technical difficulties with recording and everything, but first 3 lectures are now available. So whatever I have, I will put there, right? Right, thank you for joining, and I will stop the lectures now.